All right, everybody. So continuing sequences and series, the idea of a geometric sequence, remember, geometric sequence is really nothing more than an exponential function, uh, meaning that the variable that we're kind of solving for, where x would normally be, is in the exponent position. And that's exactly what we see in our general rule of a geometric sequence. N, which is the same thing as x would be in a function, is what we use in a sequence. Well, that's in the exponent position. Well, what we're going to be looking at in this lesson is a couple of different things. First, we want to be able to try and identify, well, what is a common ratio of a geometric sequence? Can we identify what the rule would be, meaning can we write the sequence, can we write that equation out, and we'll be able to find the number of terms of a geometric sequence. So looking here at the list of numbers that we have, negative 7 over 8, 7 over 4, and so on, what we're going to be doing is we want to identify, well, what is the common ratio? Now, the thing that differentiates a geometric sequence from an arithmetic sequence is in an arithmetic sequence, we would take the difference of the consecutive numbers, meaning I would start at negative 14 and I would subtract the 7 and say, oh, okay, the difference here is a negative 21. And then I would go to the 7 and I would subtract the negative 7 over 2 and see, oh, well, it's not the same. It's not negative 21, so uh, it's not an arithmetic sequence because we have to have that common difference, which, I continually refer to it as slope. The common difference and the slope of an arithmetic sequence are the same thing. Well, for a geometric sequence, the way that I tell if something is geometric is we look at the common ratio, meaning instead of taking the difference of the numbers from the one on the right to the one on its left, we compare the ratios, meaning I'd say negative 14 over 7 and say, oh, well, that simplifies to be negative 2. And I would do that for all of them. And I would say 7 over negative 7 over 2, that would also be negative 2. And continue negative 7 over 2 over 7 over 4, and that would also be negative 2. So here the common ratio of the sequence numbers that we're seeing is negative 2. So since we need to write the sequence here, I need to know what is a sub 1. I have to know that. I have to know the common ratio. Oops, oh my, didn't mean to erase all that. All right, well, let's start over. Smaller eraser. So we have to know a sub 1. I have to know the common ratio. And that's pretty much it as far as a geometric sequence is concerned. So a sub 1, the first number in my sequence of numbers here is negative 7 over 8, and the common ratio is negative 2. So looking here, the next thing it's asking us to do is, what is the rule? Well, a sub n would be equal to a sub 1 times r to the n minus 1 power. So substituting those values in to the generic function, I would say a sub n would be equal to negative 7 over 8 times negative 2 to the n minus 1 power. And so here are the first three things it's asking us to find. What is the first term, what's the common ratio, and what is the equation or the rule for this particular one. Now it's asking us, well, what is the 6th, 10th, and 12th term? Well, now that I know my general rule here, I'm going to say, well, a sub 6 would be equal to negative 7 over 8 times negative 2 raised to the 6 minus 1 power. So looking here, typing this in, simplifying it a little bit, will give us negative 7 over 8 times negative 2 to the 5th power. And negative 2 to the 5th power is going to be a negative 32. So now we're down to negative 7 over 8 times negative 32, which simplifies to be 28. So there's a sub 6, and then I'll do it for a sub 10 and so on. So a sub 10 here, negative 7 over 8 times negative 2 to the 10 minus 1 power will give me negative 7 over 8 times negative 2 to the 9th power, or negative 2 to the 9th power is going to give me 7 over 8 to the negative times negative 512. And negative 7 over 8 times negative 512 is 448. And so the last one that we're looking for, a sub 12, will give me negative 7/8 times negative 2 to the 12 minus 1 power. So negative 7 over 8 times negative 2 to the 11th power. And negative 2 raised to the 11th power is negative 2048. And that multiplied by negative 7 over 8 is 1792. So there are the last three things that we need. So the first thing, what is the common ratio? Second thing, what's the first term? Write the equation based off of those things, and now find some, find some numbers. What are the 6th, 8th, and or 6th, 10th, and 12th terms? So that's pretty much it for that example. Now, the next one is a little similar, but they're instead of giving you fractions, they're giving you decimals here. Essentially the same thing. But again, I want to know what is a sub 1, what is the common ratio, and what is my rule. So a sub n is equal to a sub 1 times r to the n minus 1 power. So we know how to substitute it. So looking here, if you say 0.0128 divided by 0.032, you're going to get 0.4. And if you say 0.032 divided by 0.08, remember, we're just taking the number on the right and dividing it by the number immediately to its left. And we're getting 0.4 in this case. So my common ratio is 0.4. And I'm gonna just go ahead and leave it as a decimal, since everything else is in the sequence is a decimal. You could definitely write it as a fraction if you wanted to, but since they gave me everything as a decimal, I'm going to keep my ratio as a decimal. My very first term is 0.2. So now that I know the first term and the common ratio, I'll say a sub n is equal to 0.2 multiplied by 0.4 to the n minus 1 power. So here are the first three things we're asked to identify. What is the common ratio, the first term, and the rule? So now that I know those three things, again, can I find the 6th, 10th, and 12th terms? So it's just a matter of substituting at this point. So a sub 6 in this case will give me 0.2 times 0.4 to the 6 minus 1 power. Now, some of these are going to get rather interesting. As you can see in the sequence, the numbers are decreasing. Well, exponentially decreasing numbers get very small very quickly. So looking at how small they get is we need to make sure that we're typing these numbers into our calculator properly and interpreting what the calculator's display is telling us. Uh-oh, hold on.
Julieta Nelson, if you're on campus, please report to the AP office. Julieta Nelson, please report to the AP office.
Sorry, they're making an announcement overhead. So let's go ahead and continue on here. 0.2 times 0.4 raised to the 5th power. And again, make sure you don't multiply the 0.4 and the 0.2 together. use your order of operations, do your exponent before you do your multiplication. So 0.4 raised to the 5th power is going to be 0.0124. Now I can multiply it by 0.2, and I'll get 0.002048. So there is the 6th term in the sequence. Now the 10th term, you can imagine that's going to be much smaller than that one. So a sub 10, plugging these in, I'm going to get 0.2 times 0.4 to the 10 minus 1 power. So 0.2 times 0.4 to the 9th power. And 0.4 to the 9th power is going to be 0.000262144. That is a very small number. And I'm multiplying that by 0.2, and I'm going to get 0.000524288. Or what your calculator is giving you is probably something more like this. It's probably saying something along the lines of 5.2488, and it might be rounding it at some point. It might say like 2.5 or something. And then it'll say times 10 to the negative 5th power, or it might say like e to the negative 5th power, something like that, depending on the software of your calculator. It's just giving you the scientific notation because the numbers are getting so small. We have a whole bunch of zeros there. So taking a look at our last one, a sub 12, and so if that was a very small number for 10, the 12th one is going to really be small. So here we're going to say 0.2 times 0.4 to the 12 minus 1. So that's really to the 11th power. And at this point, I didn't even bother writing out 0.4 to the 11th power because it becomes such a large, awkward number. So here we would say it's about equal to, just type this into your calculator, say 0.2 times 0.4 to the 11th power, or however you want to, if you say 0.4 to the 11th power and then say multiply that by 0.2, you're going to get something in the neighborhood of 8.39 times 10 to the negative 6th power. That basically means that we have to move the decimal place 6 spaces to the left to write it out in normal decimal form. So that would be 0.0000839, whatever else follows after the 9. So at this point, when the numbers become that small, we'll just keep it written in scientific notation, and that is fine, since that's what our calculator displays are probably going to wind up giving us anyway. Now here, this is very similar to what we did in our arithmetic sequences. At this point, what this is now, you may want to write this down, you may not want to write it down, I'm not sure, because what it's trying to do is it's trying to explain to you how do you find the number of terms, meaning n is equal to what? How many numbers are there in a sequence based off of what the first term is, what the common ratio is. Now when we did this with an arithmetic sequence, because an arithmetic sequence is basically just a linear function, we were able to rearrange the function, no big deal, nothing really difficult in order to solve for n. Well, here, if you look at the general rule of a geometric function, or a geometric sequence, I should say, I'm going to say a sub n is equal to a sub 1 times r to the n minus 1 power. Essentially what we're doing is we're trying to solve for n. We would take this equation and we would want to solve it for n. But because n is in the exponent's position, the only way that we can take it out is really by using logarithms, converting it from an exponent to a logarithm. Now, what it's telling you here at step 3, it's basically telling you, well, if it's an exponential equation, which if you look at it, you can think of it as an exponential equation, as long as you can get a common base, then you should be okay. Because if you can change it into a common base, you can set the exponents equal to each other, and you can avoid having to convert anything into a logarithm. And otherwise, if you can't get a common base, you have no choice but to kind of convert it into a logarithm. So that's kind of what it's telling you to do here. Regardless of how you do it, whether we get a common base or change something into a logarithm, we're kind of going to do the first two steps no matter what. I'm going to find out what they gave me. I'm going to divide a sub n by a sub 1 to try and isolate my variable that we're solving for, in this case n. And then we would see, well, can we get a common base to set the exponents equal to each other, or do we have to convert it into a logarithm? Now, my concern is that logarithms really have not been something that we've done super well at, and I don't want to confuse a whole lot of you by doing a lot of math that I'm not going to expect you to do at this point. Now, should you be able to solve the equation for n and get it out of the exponent by taking the log of both sides? Yeah, I would hope we could, but reality says probably not. So this is what I want you guys to include in your notes, okay? In addition to the general rule here, we want to write the rearranged equation in terms of n. Now, if you want to see the math, I'll be happy to show it to you. But for the purposes of the length of the video and the fact that we've already covered this, how to do this in previous lessons, I'm going to skip it here. But if you want to know it, by all means, this would be a thing. You know, show me how to do this either in class or in tutoring. Write this down in your notes. Say, ask Mr. Pearsley this. But let's go ahead and put it down here. Okay, I'm going to say n, and this stupid board, this spot on my board, I don't know why I keep going here, but there's spots where my cameras aren't picking it up. So here, let's put it, okay? n, the number of terms that we are looking for, can be found by saying the log of a sub n over a sub 1 divided by the log of the common ratio plus 1. Okay, so make sure you get that written down. I'm not going to expect you to show me how you convert it at this point. As long as you have it, I'm telling you, you can use it. So write down that form of it. All we're doing is rearranging the general rule of a exponential function, or of a geometric sequence in this case, so that we can find out how many terms there are. Okay, now the examples that I'm going to show you will do one of each, okay? Meaning one is going to be done in such a way that a common base is easy to get, and another one not so much. So let's see what we have here. So here, find the number of terms. We want to solve for n, all right? Now this one is not a big deal as far as trying to get a common base. Let me demonstrate what we're going to do here. So a sub n is equal to a sub 1 times the common ratio to the n minus 1 power. Now, we can substitute the values that they've given us and see what we get. So a sub n is 1 over 512. A sub 1 is 4. And the common ratio is 1/2 to the n minus 1 power. Now, at this point, what we're going to do is divide both sides by 4 to get, you know, we're trying to isolate our variable. So, pardon me, if I say, and oh, I'm looking at my notes here and I'm getting lost. But anyway, if I say 1 over 512 divided by 4, I'm going to get 1 over 2048. And that is equal to 1/2 to the n minus 1 power. So this is where we would need to say, okay, well, what is a common base? Meaning 1 over 2, that is the base of the right side. And 1 over 248, or 2048, that's the base of the left side. The exponent on the right is n minus 1. The exponent on the left is just 1. So we have to look, okay, what is the 2 on the right side? What would I have to raise that to in order to equal 2048? So let's see, I think it's going to be 2 to the 6th or 7th power. No, let's see, 12. 2 to the 12th power gives me, nope, that's too big. 2 to the 11th power is exactly right. So I'm going to change the base from 1 over 2048 to 1 over 2 with an exponent of the 11th power, because 2 to the 11th power is the same thing as 2048. So now I have 1 over 2 to the n minus 1 power. Now that the bases are the same, we can just set the exponents equal to each other and say 11 is equal to n minus 1, and say that the number of terms in this case is just 10. So that one, not so bad. Getting a common base and seeing, seeing what it works out to be. Now, in the next example that we're going to look at, finding a common base is pretty tricky, and it's not even something I would even really want to attempt. The reason why it's tricky is because the sequence of numbers that we have here is including an irrational number, the square root of 3. So again, it's asking us what is the number of terms that we have. Now, if I look here, 27 radical 3, 27 radical 3 over 81, that's going to give me a common ratio of, in this case, the square root of 3 over 3. So a sub 1 is the 243, and we want to know what is n. So this is where, if you go back a couple of, if you rewind the video if you need to, we are going to write down this reformed, or not reformed, this rearranged equation where I say n, the number of terms, is equal to the log of a sub n over a sub 1 over the log of the common ratio plus 1, because that's going to save us a whole headache of math trying to rearrange that normally, trying to find a common base. It's not something that I would want to do. In fact, when I tried working it out before, I really struggled with how you change the square root of 3 to become a 1. I wasn't able to really wrap my head around it. So we're going to just do it this way with logarithms. As long as you have this down in your notes and you can have it to refer to it, then you should be okay. So in this case, the common ratio, a sub n, is going to be 1. So this here is a sub n, that's 1. So in my formula here, I'm going to say 1 over a sub 1, which is 243, and that's going to be over the log of square root of 3 over 3 and plus 1. Now, you could probably type all of this into your calculator at one go, and at this point I really would kind of encourage it, because make sure when you say the log of the numerator, when you hit log on your calculator, it's going to open up a parenthesis. So say 1 over 243. Make sure you close your parenthesis, and then say divided by the log of radical 3 over 3, and close that parenthesis. And that would give you, that's really just going to give you the number 10. And then you say plus 1, and so the number of terms in this case is 11. And there we go. So that is how we are going to try and find the number of terms of a geometric sequence. And I want to be clear that this would work on the last, work on the last example too. So if you want to use it all the time, you're more than welcome to, because that is what the rearranged form of the exponential or of the geometric sequence is. So at this point, again, if you have any questions that you have thought of during the presentation, make sure you have them written down, bring them to me in class or in tutoring, and I will be happy to work with you on any questions that you have. But until then, guys, thanks as always for watching, and we'll see you in class soon.